So, good morning. We were last time exploring the nature of the equilibrium point of linear systems in the two-dimensional case. Of course, this general theory can be extended with all complications that the dimension increase would bring, but essentially most of the properties can be predicted. And some of the properties can be easily predicted. Yeah.
Sir, can you put
Yeah, is it?
mic off? Yeah, done.
Yeah, I have switched off the mic. Yeah, sorry. Yeah. So you can generalize it to higher dimensions. There is no problem. But the problem is when you work in higher dimension, there will be some additional complications that would come up. But essentially, the main features will remain the same. I'll just make a remark or so towards the end of it. But we'll get a feeling of what goes on. And where we stopped was this. We were looking at this system. And we assumed that the determinant of is not equal to 0, which implies 0, 0 is an isolated singular point. Or x identically equal to 0, y identically equal to 0 is a sort of singular solution of the system, and this is the only singular point that you can see. Okay, there are no solutions for ax plus by equal to 0, cx plus dy equal to 0. Okay, so this is the only solution. And as I said last time, that if x naught y naught is a solution, if a, b, c, d are such that, you see, you have got yeah, so if you have something like ax plus by plus say x1 equal to 0, cx plus dy plus x2 equal to 0, and then you have the singular point that you can compute from what you call pxy equal to 0, qxy equal to 0, where these are linear expressions. P and q are linear expressions. Then you see that you can always introduce a change of coordinates or shift the origin to the point where P and Q vanish, and then what you get will be a sort of analogous system with 0, 0 as the singular point. So without loss of generality, we assume the system has 0, 0 as a singular point. And in fact, the way in which we have chosen, that is the only singular point. Now we assume, so we have considered several cases. Now we assume the eigenvalues are lambda 2 are complex. That means, let us take it specifically, lambda 1 you take as alpha plus I beta, and lambda 2 is then, because of the nature of the problem, all are real coefficients, etc. Lambda 2 is equal to alpha minus I beta. Okay. there of course alpha is equal to a plus b by 2 and beta square equal to minus bc minus a minus d therefore you know that beta square is positive since you know this has to be complex, that beta has to be different from 0. So beta square is positive. Beta square is positive means negative. So that's a consequence of this. This will be relevant to our analysis. That is, in such a scenario, you have B and C such that BC is negative. Okay. Now, let us first take the case of vortex points. I think this is what I was doing last time, where this corresponds to alpha equal to 0. That means the eigenvalues are purely imaginary. That is given by plus I beta and minus I beta. Now, you immediately see that suppose the eigenvector, suppose Z1, Z2 complex valued is an eigenvector associated with I beta, that is lambda 1. Then Z1 conjugate Z2 conjugate is an eigenvector associated with minus I beta. So from this, I mean, these are complex numbers, therefore what are the corresponding solutions? We can write down the complex valued solutions. The corresponding solutions are, okay, let me take Z1 equal to x1 plus I y1, Z2 equal to where x1, y1, x2, y2 are real. Then what you have is that corresponding to lambda 1, the corresponding solution is going to be e to the power beta t corresponding to lambda 1, and corresponding to lambda 2, the corresponding solution is going to be now you expand it and write down in the form. Now this I can write as the following. So then equal to, I am just writing it, you check it up later, and if there is anything you correct it. So this is x1 cos beta t minus y1 sin beta t, x2 cos beta t minus y2 x1 sin beta t then y2 cos beta t plus x2. Similarly, you can write for, it will be something of this type. So if you take real solutions, I am skipping a step, hence, see these two real solutions, these are real solutions of the problem and they are linearly independent solutions. So they form what you call a fundamental set of solutions for the solution space. Therefore, x1 cos comma they form a fundamental set of real solutions of the problem, and that's what we are looking at. Therefore, every solution is a linear combination of this. Therefore, a general solution of the problem is what is it? It's of the form, I think I'll write down the simplified form. D, where C and D are arbitrary constants, and yt so xt yt is the characteristic. C of the same thing with x2 cos beta t minus y2 sin beta t plus d y2 cos beta t plus x2. Anyway, now simplify it. You can see that this is of the form. So this is of the form I'll simplify it, and the constants you can work out, the exact constants you can work out. I leave it to you to do that. It is of the form xt equal to, not this, the same c. So let me call this, if you want you can call this, say, okay, a tilde cos beta t yt equal to c tilde cos beta t plus d tilde this is of the form. Now you just work it out and then collect coefficients of cos beta t, sin beta t, etc. It will take this form where a tilde, b tilde, c tilde, d tilde are constants. Okay. Now eliminate t between them. It involves solving for cos beta t, sin beta t, and then using the magnificent trigonometric identity, namely x cos square beta t plus sin square beta t equal to 1. And that gives you something like this. If you do all the simplifications, then this is what you end up with. Yeah, it will be c tilde x minus a tilde y whole square plus d tilde x b tilde whole square equal to whole square. So this is the equation in the xy plane of the particular curve that you get for different values of c tilde, a tilde, or corresponding to whatever c, d, etc. that you use, you will get different curves. What is the nature of this curve? You can easily see that you can transform this by putting cx plus a tilde y equal to capital X and this as capital Y, and then you get, if that is the case, you get x square plus y square equal to some square. So with that transformation you get circles, concentric circles. But in the general scenario, you see that you can observe that this corresponds to an ellipse. Okay, so let me just show that. What is that you have to see to find that it is an ellipse? You know the second degree equation, second degree homogeneous expression, and something of the form ax square plus 2hxy plus by square, that represents an ellipse or say or hyperbola or parabola, depending on the sign of the discriminant. Okay, so let us use that. Now one can show that if you work this out, the discriminant, okay, if you expand this, right, you can expand this. This is of the form, okay, you expand this, it is of the form, say, okay, what notation I should use? Okay, it will, I'll write it. So if you expand this, this is what you end up with. I presume my calculations are right, but you can check. independently. Minus 2 A tilde C tilde this is the quadratic form. Now this is equal to C tilde B tilde minus A tilde D tilde whole square. Now this is the quadratic expression that turns out. I see that one can check that the discriminant the discriminant is this. Suppose you have got ax square plus 2hxy plus by square equal to 1. Suppose you have an equation like this. Now what is the discriminant? The discriminant is, see, the nature of this one is governed by what this is, that is h square minus ab. If this is negative, then you know that it is an ellipse. Okay, so we prove that in this case this is so, and you get the discriminant is actually is given by minus C tilde B tilde A tilde whole square, which is less than 0. Therefore, this represents an ellipse. Okay. So, for different constants that you choose, you get different ellipses. So, you end up with something like this. In the xy plane, and the center of the ellipse is 0, 0, you get paths of this kind. They are concentric ellipse. So, each of the characteristic curve is something, you know that no two characteristic curves can intersect. Therefore, you see that all the characteristic curves are of this type in this case. And what is that you can say? You can say that none of these characteristics approach the equilibrium point zero zero plus or minus infinity. Okay, and therefore there is no question. So naturally they do not enter the particular singular point. So this is the singular point that you have. Okay, so this is something like the solar system that you have, where you have a equilibrium point, and around that there are orbits of this kind. Okay, so if you are on one orbit, then you just start moving around that elliptical orbit that is passing through that point. There is a unique elliptical orbit that passes through that point. So when the eigenvalues are purely imaginary, then you end up with a characteristic curves of the type which are elliptic and centered around the equilibrium point, or you see that this is the situation. This is what is called a, in such a case, 0, 0 is called a vortex point. Just if you drop a particle, so it's something like there is a flow around a point, and what happens is you drop a leaf or something like that floating, it just takes the elliptic path that passes through that point. Now that will be the nature of the motion around a vortex point. Okay. So now what we do is we go to the generalize this. Okay, one more thing that we have to do. So natural doubt that creeps up is in what direction you will be moving around. Is it always counterclockwise or clockwise? Now this is where I think the condition that we wrote down initially, we have BC because we had the expression, namely, what was the expression? The expression was, beta square equal to minus BC minus half of A minus the whole square, and beta square is positive, therefore BC has to be negative. Okay, so BC is negative, right? So this is the situation that you have, and if this is not true, then you cannot have the eigenvalues purely imaginary. So if you have these eigenvalues purely imaginary, then necessarily this BC is negative. What is the implication of that? Let us see. And that would help us to decide on the direction in which the motion takes place along these orbits. It's a very fascinating how you read a lot of things from the equation. So what is the equation? The equation is this. This is the equation. And what we have seen is that in this scenario, you have BC negative. BC negative means what? If B is positive, then C is necessarily negative. I mean, both B and C have opposite signs. Okay, they cannot have the same sign. So there are two possibilities here. Either B is positive or B is negative. And correspondingly, C is negative. So they go together and these two go together. So that the product is always negative. Let us now work on that. What happens? Now you see, you have recalled dx by dt by. Let us take the first equation. Now we will see how x changes as the characteristic crosses the y-axis. So on y-axis, you take some point, say 0, y1. It's an arbitrary point somewhere here. Then what happens? See, we look at this one. dx by dt at 0, y1 is equal to simply B y1. Now we are taking y1 positive. That is in the upper half plane. Then what happens? What is that we are assuming? We are assuming B is positive. So if B is positive and y1 is positive, then what can you say about by1? By1 it is positive under these conditions. What is the meaning of that? X increases with the time, that is the x coordinates. See, at this point you have xt, yt. The xt corresponds to x coordinate, yt corresponds to the y coordinate. And what is the behavior of xt? The behavior of xt is that x increases because this is positive. So x increases at y1 if y1 is positive, b is positive. Then what happens? That means the path is crossing like this in this direction because the x coordinate has to increase. So it is moving from third quadrant to first quadrant. So every second quadrant to first quadrant along positive y-axis. So all characteristics are what you call clockwise. You can do the same analysis with the C. In that case what you do? You look at the x-axis. Take some 0x1 and see what happens. You see that if you assume B is positive, then C has to be negative. And look at the change of y along the x-axis. Okay? So you take a point 0 x1 positive, and then you see that you look at this equation. What is that? Dy by this is the equation that is to be considered. Dy by dt cx plus dy. Sorry, it is x10. I'm sorry. So y coordinate is 0. Now you evaluate this at x10, and then what happens? You end up with cx1, and we are assuming x1 is positive and c is negative. Therefore the derivative of y with respect to t is negative. What does it mean? Y decreases, which means the characteristics are moving from first quadrant to the fourth quadrant. And similar analysis you can do along this one. So to fix the direction, so you see that the condition BC is negative actually fixes the direction. If you change the condition B negative, then you see that what happens? So this is for B negative. If B is positive, then all characteristics move from counterclockwise direction, that is positive direction. Same analysis, through the same analysis you can, so the direction will be reversed. So whether the objects move in the neighborhood of 0, 0 in the clockwise direction or counterclockwise direction is completely determined by the sign of B or equivalently the sign of C, because you know that this condition has to be satisfied. Okay, so that's the most interesting part. So we have, you can extract a lot of information about the characteristics without really solving them. Okay, now let us go to yeah, I wanted to say something more, but I keep forgetting it. Right. Yeah. Then about the stability. What is the definition of stability? The definition of stability is the following. Given epsilon positive, there exists a delta positive such that if xt yt is in the delta neighborhood, of 0, 0 at t equal to t naught, then it will stay in the epsilon neighborhood of for all the time. Okay, so what does it say? Okay, let us take an elliptic orbit. Now I just explain it out. Yeah. Draw another picture, so that's better. So what this tells you? See, generally this means the following. Suppose 0, 0 is the equilibrium point. And suppose there is a characteristic. Okay, what you say is, given epsilon, take an epsilon neighborhood of this. Then what it says is there is a delta neighborhood there is a delta positive such that once xt yt is here, say somewhere here, so this is the point xt yt, xt naught, at t naught the particle is here, then what happens? It just stays in the epsilon neighborhood. It will never go from there, or it can never escape there. So it will be, say it may be even, I mean, now this is the vortex case that I have seen, and you see that this is always true in this case. But even if it is not something of this kind, you have the epsilon neighborhood, then you have a delta neighborhood, such that once the particle is at this point xt naught yt naught, then see the orbit will be always somewhere here, whatever be happening, it will remain in the epsilon neighborhood. It can never escape from the epsilon neighborhood. This is what you mean by the equilibrium point is stable, that every path or every characteristic that enters the delta neighborhood at the time t equal to t naught will continue to stay in the epsilon neighborhood. Remember, for each epsilon you can find a delta. Now you also make another thing very clear. See, although you see this xt naught yt naught here, it may get away from the delta neighborhood. But what you want to say is this, that it stays in the epsilon neighborhood where the delta is fixed according to the epsilon. Then you say it is stable. So this is what you call a stable neighborhood. Okay, and then there is another expression called asymptotically stable. If it is asymptotically stable if it actually enters. So here you see, none of the in the vortex case, none of the characteristics are approaching 0, 0. But here, if it is also entering the singular point, then you say it is asymptotically. This is, I mean, true for all characteristics. Okay, every characteristic that enters the delta neighborhood will stay in the epsilon neighborhood. Not only that, they all enter 0, 0. Okay, if that happens, then you say it is asymptotically stable. So there are two such expressions. So you have another terminology called so this is the situation that you have for when alpha is 0. Now we take up the case where alpha is not equal to 0. Let us see what happens. How do the solution looks like? So when alpha is not equal to 0, you see that lambda 1 equal to alpha plus I beta, lambda 2 equal to here again BC is negative. That is a general case situation. It does not depend on alpha, depends only on beta. because beta square is positive. From that you get this relation, that is BC is negative. So B and C have opposite signs in this case. Okay, so this is the general conditions that you have. Now what are the solutions? The solutions are again the same kind of solutions that we have looked at. See, xt is you are writing down the real solutions. So the real solutions are going to be e to the power alpha t into that linear combination of cosine and sine factors. So something like a cos beta t yt is equal to, this is what it will come out to be, where a and b you have to compute from the situation. So it is going to be e to the power alpha t so this ABCD you will have to work out. Now this part, see, this part essentially you have seen that it sends the particle to go around. Okay, as t increases, what happens? If you consider alpha equal to 0, then what happens? This gives an elliptic orbit. But what happens to this? Now let us take the situation alpha is positive. If alpha is positive, see, as I said, this sends the particle around this direction. So let us assume that it is moving in this direction. That means that is corresponding to, we have seen this is B positive. No. I think B negative. Because counterclockwise. Counterclockwise is B negative. Oh. Sorry. I wrote it wrongly here, I think. I think there is a mistake here. So I was taking this one positive and this is negative. Right. You just note that correction. Okay. So because you can see that dx by dt along 0, y1 is b, y1, if b is positive and y1 is positive, then you see that this is positive, so x increases, so you are moving from second quadrant to first quadrant, right? So I am sorry, I wrote it wrongly here. Okay, so this is the scenario. If B is positive, then you are moving in this direction. Okay, now what happens? What happens here? Alpha is assumed to be positive. So as t tends to infinity, what happens is, see, the radius vector will be increasing. So each time it goes round, it goes farther and farther. So the situation that you get is something like this. See, it goes round like this, then it goes farther away, and so on. Okay, so when alpha is positive, B is positive. This is the kind of scenario that you get. I hope you get the point. because of the presence of this. Now suppose alpha is negative, then what happens? So we have, let me draw the picture. So I'll first take the case alpha positive, B positive. Then the picture is something like this. Okay. What happens is, since B is positive, it is moving in the counterclockwise direction. But since alpha is positive, it is moving away from 0, 0. So this is the path it follows. Okay, that's what I have drawn there. So here, when alpha is positive, every characteristics moves away equilibrium point. So if you have another characteristic here, it also has this property, because no two characteristics can intersect. So it's all filled with characteristics, but they all have a motion like this. But what happens is, as time elapses, you see that if you have a particle starting from here, you will see this particle running away from there. So you consider this as a what you call a spiral point. So this is what is called a spiral point. Sometimes it is called a sink, a source. You would have seen in these, whirlpools in the river, where you see this kind of motion is there. You see that in some cases the whirlpool will carry things inside. Some cases it will just throw out things. Okay. So this is a scenario where you have instability. It is unstable. This is unstable. And this equilibrium point is an unstable equilibrium point. So it is unstable, counterclockwise movements. No, I am making a mistake. Sorry, this is clockwise movement. What I have drawn is now you take alpha negative and B positive. Then of course it is quite easy to see. The direction will be governed by B, that is sign of B, and you see that the direction is again clockwise. But what happens is, every time it goes round, it gets closer and closer to the equilibrium point. Doesn't stop there, it just this is the case where alpha is negative. So 0, 0 stable equilibrium point. 0, 0 is a stable equilibrium point, and all characteristics approach 0, 0. Why? As t tends to, see, you are taking alpha negative, as t tends to infinity, then this part will pull it down to 0. So xt goes to 0. Okay, and of course the direction is determined by this. So this is clockwise. Okay, now you can write down the cases where alpha is positive, B negative. Then the situation is this. This is 0, 0. Now you see that the movement is now counterclockwise. So what you have is this. It runs away. This is counterclockwise movement. And it runs away. So then you have unstable spiral point, counterclockwise, or movement. Okay. Now the last case, the fourth case is the following. You have B negative, but alpha negative. Then what happens is the picture that emerges is this. You have again counterclockwise movement, but then something like this. As it goes around, it comes closer and closer to the equilibrium point. This will be the nature of the path. Okay, this is stable equilibrium. All characteristics approach 0, 0 plus infinity. And the motion is of course counterclockwise. So this defines, or this completes the analysis of all these cases. Now I'll just sum up finally and then leave it at that. So let me sum up. And you can easily see that yt by xt in all these cases does not exist, because you see that e to the power alpha t will just get cancelled, and then you see you have a expression whose limit does not exist as t tends to plus infinity or minus infinity. Okay, so let us sum up the equation. So 1, if lambda 1 and lambda 2 real and have the same sign, then this is called a nodal point. That's the first case that we have considered, in which if both are negative, then you see that the all characteristics will enter 0 0. If both are positive, all characteristics will leave along certain paths from the equilibrium point. The second case is lambda 1 opposite side. Then what you have? A saddle point. So this is lambda 1 less than 0, less than lambda 2, say. Then you see that see, one of the characteristic enter along the eigenvector corresponding to lambda 1, and all other characteristics enter along the direction. Okay, there's only one characteristic, T-linear characteristic that goes to, that enters 0 0. All others will run away from that, because you have this kind of scenario. There's a path along which you see that the characteristics will enter. The other path, now you see that all you have is this. This is the sort of saddle point that you will take. Then of course the cases that we have just now considered, namely then this corresponds to what is called vortex points. Then 4 complex. That is, we are assuming alpha not equal to 0. Then what you end up with will be a spiral. And you see that in these cases, BC, the sign of BC is relevant to determine the direction along the characteristics. So I think I'll stop here. Then we will come back at 12 o'clock. Thank you.